Hello, everybody, and welcome to Module 4, where we are having a closer look at some design parameters. So, just as a recap, what we have looked at so far, what we have learned is some basic mycological terminology and processes, some cultivation techniques like working with agar, working with grains, what is liquid culture, even the basics of just what is mycelium. We have also gone through various substrates that you can start off experimenting with and how to prepare those for the kinds of materials that you want to use and why you would want to choose different substrates for different types of designs. And then we also had a look in our last module at composites. What are they? How do we make them? In general, myco-materials are predominantly composite materials. They involve two different materials, right, that we're putting together. It's our mycelium with a food source like an agricultural substrate or a fabric or something like this that we are joining together and making one product or one item that is sort of stemming out of the two that is completely novel from the properties that alone either of those other components could have had. So it's really interesting to work with microcomposites and just to understand the materials that you're working with and see where their potentials are, see where their faults may lie, and then try to marry some materials. Especially here, we're talking about mycelium, but this could be with a lot of other material practices as well. Try to marry some of those materials that could complement each other in those places that they're lacking. And so, just to present our collective once more, for those of you who don't know us and are just joining us now, we are Jessica Diaz and Catherine Uwali. We are a collective of researchers and artists that work with mycelium and also many other living organisms. But here we're focusing on mushroom mycelium to create various different forms from flexible materials to sculptural materials to just crafting and playing around with this material for fun and understanding some of it to doing some more specific research on some of the properties, in particular techniques and applications of mycelium as a material that is either flexible like a membrane or that is architectural. And those are kind of our backgrounds and our focuses at the moment. And so diving right in, this is kind of a segue from module 3. I think module 3 and module 4 really go together. However, they're quite long to put together in one space. So, and a bit dense as well. It's a lot of information to take in all at once. So, here we are starting off right where we left off with composites, and I just gave you a brief description of what that means. And with 3D printed substrates, what normally you're looking at is a cold extrusion of a paste. So unlike regular 3D printing, which involves heating up a plastic and onto a heated surface as well, and then printing a plastic or PLA filament, then in this case, you are not heating up your paste because you will kill the mycelium. So this needs to be a cold extrusion. This means normally you have a large tube where you're going to fit your paste, whatever the mixture of that is. Normally, for the most part, what's being researched and what's being used and what we have dabbled in as well has been a mixture of clay and mycelium. However, you can also add cellulose, which can be from recycled coffee cups like Blast Studio does, or it can be from other types of paper or cardboard sources that you will pasteurize all together. You will boil them, make them into a paste, kind of like as if you're making paper mache, but you're not using a glue. Your binder is the mycelium, right? And then the clay is like the structural property that allows it to not just be a gloop, it allows it to actually stay up as the layers are being built by the extruder, which is super important. Another thing to note with the 3D printed paste is that the nozzle needs to be quite large. You can do this with the smaller nozzles that are sometimes used for clay in some more delicate forms. However, the larger nozzles are ideal. Then you can print some larger structures that accommodate all of this paste and allow it to just have a more structural integrity as it builds up. And so here, this is a sort of case study for you all. I think this is a really good project. You can find the PDF documentation of this and sort of follow along. This has been really helpful for myself into experimenting with some paste, and as well as Jess has experimented with some clay only paste, and this is the same principle. So this project is called Pulp Faction. It's a project that uses this method that I mentioned here called paste extrusion for printing mycelium. It's inspired by termites, which you'll see in a little moment. I'll show you what that means or what that looks like. And they're mycelium built tunnels. So using form, as you can see here, there's like various labyrinths. It's folded in many spaces. It's non-linear. And this is a lot of what you'll see when you are printing mycelium. There'll be a lot of folds, or the geometry of the shapes won't be so linear because that geometry keeps a microhabitat of humidity between the folds. And so it actually, the form allows the mycelium to grow better without having to input so many external factors like more humidity, more temperature control from whatever electronics you may have in your space that are controlling that for you. So it's really interesting to think how we can use form to actually be the drivers of that environmental control for our mycelial growth. So this is biomimicry at its best. The reason why it's inspired by termite tunnels is that in termite tunnels, the mycelium provides structural support to their tunnels that are made with sand and clay and whatever else is in the soil. And it acts as a natural adhesive, as we had mentioned before. This is what mycelium does in nature. It actually binds and holds soils together. And this symbiotic relationship with mycelium enables termites to create intricate, stable, and environmentally controlled tunnel systems. So it's also great for the termites because they will have more heat being produced and more humidity being produced in their tunnels and in their living spaces. So how do you do this? Well, for 3D printing, you need a composite pulp mass. This pulp consists of a substrate that has been seeded with the fungus. So basically you're using either an agar plate that you're going to blend into your paste right before, you need to do this right before you're going to do the whole process. You can let it grow a little bit, but there's no need. You just need to make sure that your culture is like fully myceliated before you do this. Then the substrate is primarily include fine wood chips, paper pulp, and clay. The wood and paper pulp make up for most of the material and provide the nutrients for the fungus. As we have covered extensively, this cellulose is what our fungus, our mycelium is looking for. The clay is acting as a structural component to allow it to be able to extrude on itself layer by layer by layer and not collapse. So exactly that is the point here. It acts as a binding agent to stabilize during printing. And then this is what the termite nests look like, or labyrinths. So in termite tunnels, as I mentioned, the mycelium provides the structural support. And here you can see how the symbiotic relationship in the actual form of this termite tunnel um, has inspired a lot of that work with mycelium printed pastes. And if you look at some other examples that are now they're becoming more easily accessible, especially because clay printers are actually available now. You can purchase a clay printer, which is something that I found out only recently. Before, you had to hack or either build your own clay printer. And by before, I mean even a couple of years ago, I remember making or playing around with other people's clay printers who were making their own clay printers. And this was in maybe 2018, 2019. So the technology has really advanced quickly, and this became a really popular field. So the niche was there to be filled. So you can buy your own clay printer, which will make it so much easier for you to be able to extrude your shapes, as long as you know a little bit about digital fabrication. And if you don't know how to make 3D molds on your computer, that's also fine. You can find first references, like have a look at what these structures look like, and then start small. Also, like, just measure out your scale so that it is not massive, just in case this doesn't work, and print out a few different times and a few different types of forms so that you can document which one works better, and then sort of select that appropriate one to continue scaling. And yeah, so instead of having to hack like a regular PLA or plastic filament heated extrusion printer, you can now just purchase a printer. And you can also, if you don't have access to that, you can try to play around with this with a syringe. If you have like the 20 milliliter ones, at least with the big nozzle, they do have to have like a big opening. It works best that way, and see what comes out. That's a good way to start prototyping always, especially with extrusions of biomaterials. I think just using a plain old syringe is the way to go, and then try to scale up and either hack your printer or use a printer that works for your biomaterial. Because although there are clay printers, of course there aren't printers for like all types of mixtures, so you have to make sure that the parameters are going to work with the type of recipe that you're going to put in there. This recipe works well. However, yeah, there are like other gellants and things that you might put in there that might not extrude as easily, and you might have to try a few different parameters for speed, for instance, and for pressure that will allow you to just see what works and what doesn't. And density also of your material. Maybe you have to add a little bit more water or add less clay if you find that it's really dense and it's not coming out of the nozzle, it's not extruding. And here's another way that you can 3D print. This is a wood-based filament, and this was a student of the Fabric Academy course that I was also a student of back in 2018. Tobia Chechin, or Chekin, I feel like I'm saying that wrong. Sorry, Tobia. Um, he came to me at some point to try to work together on making this shoe. And it was a really interesting shape. As you can see here, it's almost like resembling that same idea of these labyrinths. However, in this case, that's not really necessary. Why? Because in a 3D printed substrate, like grole, which is what this is, it's a wood-based substrate that is called grole. If you're trying to find this online, that is what you should look for. And basically, it's held with a sugar, like a glucose binder. And once you extrude it, and you use a regular 3D printer for this, I should mention. So there are instructions. Once you buy this filament, you should follow the instructions to be able to print this well. Because what tends to happen um, with these biofilaments, let's say, for that are made for regular 3D printers, like there are also algae ones like Algix, they tend to be quite tacky. And so your nozzle might clog. And we have definitely had this happen and had to like replace the whole nozzle. So one trick for these, particularly for this wood one, is to actually dehydrate it before you use it. You can put it in the oven for a little bit and then allow some of the water content to leave. Then you can print it out, because that is what's making it more tacky, is that sometimes it absorbs water. That's really what it's made for. It's made for absorbing water and humidity, and that's why the mycelium can grow through it, because it's wood based, first of all, but also because it can hold humidity. So first, dehydrating is great. And if you have a dehydrator where your entire filament roll fits into, amazing. If you don't, in a conventional oven, you can do that. Then you will find the settings that are recommended by Grolay to print this filament, and you might have to fiddle around depending on your printer. It might be finicky to get this started. It's good to always put like some kind of adhesive on the base of your 3D printer as well when you're printing, so that especially because it's a kind of a tacky material as it is, that as the upper layers are extruding, they don't pull the whole base of the first layers that you've already extruded onto the base. And so what I was mentioning before about the shape is that exactly that this already holds humidity. It's already made for that. So there's no real need, aside from aesthetic reasons, to make this shape. However, it's really beautiful, and it made a really cool sole of a shoe, because it actually almost worked more like a mold than it did. It did both, but in different ways. So the sole worked more like a mold, and then the upper part actually penetrated. The mycelium actually penetrated, so it was myceliated, and it grew a skin. And I will show you in a second what that looked like. So basically, Grolay, not Growly, sorry here, Grolay filament is like your substrate, like your means of growth for your mycelium, because it has a lot of porosity as well. It's very porous. It has like microcapillaries, and that means also that you can grow other things on there. You can grow seeds, actually, you can sprout seeds. So there are little spaces. Once you submerge this, the spaces will open up. So one thing at a time. I'm getting ahead of myself. We've printed out the shape that we wanted. Normally, if you're making something big, especially with these kind of experimental filaments, is better to consciously cut your piece into a few different modules or a few different pieces that you can then bind together. It'll just make it so much easier for your printing process if at some point the nozzle clogs or something happens over time, to make the printing time shorter. So just to make smaller pieces and then put them together. So once you've printed that out, you need to soak this for at least like 12 hours. And this is going to allow the material to look like this. Now you can see this is a bit bloated. It looks a lot more soft, and it is. It's very soft once this happens, which is so interesting. This is a very interesting material to print with, because here it's very, very hard and brittle. And then once you soak it, it's very like spongy, and it even changes color. And then that it holds that humidity in, that sponginess, that porosity of this material, allows the mycelium to work itself through. And actually, you can see here how it's like not just growing through the layers, but it's actually growing through the material itself. It's finding its way into the pores and growing on the other side because we inoculated it from the inside, as you can see, and now then it's growing out from the outside. And there's different textures here. So some textures that are more, you can see sort of separate layers happening, and then you can see this kind of like wavy structure. And then there are just flat layers, very smooth layers that don't have all that texture, to see how it would grow on both. And this is kind of what that looked like towards the growth phases. Um, this was using a Ganoderma strain, and it started growing a skin over top that started sort of from the bottom space where we had most of the mycelium. We didn't really fill the whole thing. I mean, here you can see, oops, here you can see we had filled the whole thing, but that was a sole that we were creating separately. This was a different piece. So from that sole, this started to grow upwards, up on top of all these columns and little squiggles, and start to make a membrane. And here are just some suggestions if you're using Grole, what the parameters are for temperature and also for the types of adhesives that you could use. And then you dehydrate that piece like anything else, any other material that you want to dehydrate. Other ways to use 3D printed substrates are not by using cellulose-based substrates at all, but by using synthetic substrates and using mycelium as a hinge or binding agent between modular pieces. So talking about modular design, this basically means pieces that of a large structure that is made up of geometries that all fit into one another, like a lock and key or like a puzzle. However, these pieces are all repetitive and they all have the sort of male and female, as you would call them in design, but yet just like the positive and negative tabs that link onto one another. And here, this project by Jess was the hyper-articulated mycomorph, her thesis for her architecture course at EAC. And here she used PLA. As you can see on the right, this is a render of what this form looked like. This is meant to be a table. And you can see that she printed these pieces all separately, separate small pieces, and started at a smaller scale, then worked her way up to a larger scale. As you can see on your left, that's a larger piece that has been inoculated and has actually been incubating and growing. And basically in the spaces where the separate pieces, separate modules fit into one another, that is the spaces where she designed a hinge or a space that she could inoculate and then fit the next piece on top that also had that inoculated space with mycelium. And the mycelium will actually grow into itself and it will bind to the mycelium in the other piece and it will create a natural bridge or hinge between both. So that's another interesting way that you could use mycelium, especially as a means of like something artistic. And this, if it's a table, you could even let it fruit and it would be like your table and also your food source at the same time. And so what do we need to keep in mind when we are designing molds with a 3D printer? We need to, or without a 3D printer in general, our molds can be designed out of almost anything. We can design them out of cardboard, out of wood, out of foam, out of silicone, plastic, even fabrics in 3D printed forms, as you have seen so far. And with large forms in particular, The key is to design openings distributed around the mold. This will allow airflow and guarantee uniform growth throughout. What that looks like is this right here. So basically, this is a tiny, like um, quarter scale surfboard. And this is how you should start always when you are designing something. Make a lot of small tests. Quarter scale mock ups are great. So, this is a quarter scale mock up of a surfboard, and it's not huge, so there are only 6 holes along the surface, but that is great. And you have to actually, I mean, you could drill that into, but like, why would you necessarily need to drill that into your mold? You just can add that into your 3D design before you print. And those are there for air exchange. So another thing with 3D printed molds is that these molds are super rigid normally, unless you're printing with like a Filaflex or something like that. It's a flexible filament. Um, if you're printing with PLA or any other plastic filament, then your mold's going to be very rigid, and you will need to put a membrane between your mold and your mycelium substrate piece, because you won't be able to lift it out afterwards. So once this is fully myceliated, this piece to like the left side of the mold is where the substrate with the mycelium is, right? It hasn't grown yet. It's like brand new, inoculated, and put into the mold. You can see that there's a cling wrap on top of it, and that's really important. That's what's going to allow you to lift it up, because once it's fully myceliated, it's going to still hold a lot of humidity. It's going to still be really soft. So the dehydration process is what really solidifies the material. When it's still just out of incubation, you need to be really delicate with how you're treating that material. And here's a half scale, so just sizing up. This is like a hand board. And this has been made instead of in a 3D mold, which if you're starting to scale up, this might not be what you want. You don't really want to use a 3D printer for creating large molds. It doesn't really make sense. It's a waste of a lot of time, energy. Um, and material, really. You can use vacuum forming to basically melt and form a thermoplastic sheet over top of a pre-existing form. In this case, this is, a handboard that is already existing, and then using a vacuum forming machine, you can add this thermoplastic to the machine. It will suction from the bottom with a lot of strength. It will heat the bottom surface so that as the the sort of vacuum suction is happening, just as you would vacuum seal something, it's the same kind of idea. Just suctioning all the air out, it will form the plastic around the object that you've put in there, and then it will cool. And then you have the object shape that you desire. Then all you have to do is place some holes. You can just heat up a needle if this is plastic and poke them through, and then put some micropore tape all around. The micropore tape, again, is a tape that allows the air exchange to happen while not letting harmful bacteria and other contaminants into your design, into your mold. This is what that looks like in a couple of different steps. So with the thermoformed plastic, it is easier to pull it out. You don't need to use a like cling film or something like that between the mold and the substrate, because normally the thermoformed plastic is quite soft, or you can get softer kinds, and you can pop it out. It will be rigid enough for you to do that. It just sometimes isn't rigid enough for you to pop it out of something that isn't flexible itself. Like you could sort of push the plastic forward in this case, and the whole piece will come out easily. And here you can see that piece dehydrated in the middle, and on the right you can see that piece sanded, which we will talk about later. But you can sand your pieces, and there is a, in this case, synthetic resin that has been added to the top, and that's also why it looks quite shiny. So adding finishes to your mycelium form, you don't have to keep it just as is. And here is a version of that board scaled up. As you scale up, it's also important to know that it becomes a lot easier to get contamination onto your microcomposite because you're working in an open space normally. It's hard to fit a huge, in this case, a surfboard into a sterile workspace. You can try as much as you can to have spaces that are sterilizable, like you can have a metal working table, for instance, like here, or a plastic cover that you can spray with 70% alcohol and then um, do your molding process. But also it's important to act quickly or work quickly when you're working in open spaces like this, especially if you don't have like a particularly strong strain of mycelium or you're just experimenting. There are definitely some commercial grow kits that you could do this with, and you really wouldn't have to bother with where you are in your home or in your lab. They You could work for an hour on this piece and it would not really be hindered by that. And then I wanted to look at scaffolding. This is from the University of Newcastle. It's quite beautiful. This just came out this from the hub of the built environment, I believe. A scaffold made of textiles, that these tubes basically that you see here that have been filled with inoculated mycelium substrates. And so something else that you can do is use fabric as formwork to make your piece. Meaning, in this case, for instance, this fabric is stitched along the sides to make spaces that, when filled up, make these sort of tubular pathways that you can with a lot of effort. I'm sure this isn't an easy task to fill all this up completely with myceliated substrate all the way through, but you can do that. And then in a space, in this case, quite large, to allow the mycelium to fully myceliate through the textile that you chose and through the form. You need to have the right humidity, temperature, darkness, all the other things, right? So it becomes definitely more and more difficult and more of a design challenge. Not necessarily difficult in a bad way, but just you need to think about these things, like how big is the piece that you want to make and how small can you start, and how much is that small scale um, prototype informing truly what the large scale making is going to be like. Because of course, if you did this in a small scale, it would not present a lot of the challenges that this large scale model would present. But it's a good time when you're prototyping at small scale to start thinking about what the potential challenges will be when you start to scale up, and scale up gradually. So, scaffolding can mean fabrics, and scaffolding can mean just anything that your mycelium can grow on and gives it shape. So, it allows the shape is made by the scaffold, and the mycelium is just part of that composite that you're making. Unlike in your molds, where yeah, also it's similar, but you're not keeping the mold at the end. So in the scaffold, normally you do keep the substrate scaffold in the end. You keep that structure. And so if you use cellulose substrates for making other kinds of scaffolding, then you can think about using cardboard, which is available and accessible, and a laser cutter, which is actually normally one of the most accessible. Well, aside from 3D printers these days, but it's pretty accessible to find laser cutting services around as well if you don't have one of your own. And so this was made on the left, this mannequin with a 3D mannequin shape, basically from a software called Make Human. You can actually even make it to your own size because you can adjust the human form as you like. And then once you download that 3D STL file or object file, then you can bring that into another software called Slicer for Fusion. And what this software does is that it slices that 3D shape into many many grid-like pieces. There's different structures that you can make, but they're all interlocking pieces. So you always have a vertical and a horizontal line going into one another. And it just depends on your form what you will end up using and what interlocking pieces work best for you. In this case, because I wanted to fill this mycelium mannequin with mycelium substrate, the easiest way to do that was to make this a grid. And this project here to the right is not mine, but it's also from IAG. It's called Growing into Form, which is actually exactly what is happening with a scaffold. And this just illustrates well the process that we also took for making this mannequin. Just filling up all the pieces once you sterilize the cardboard once it's been assembled. So assemble the shape first, then sterilize. You can use like a bleach spray, which I believe is what we used, and then allow that to dry. But you can also use 70% alcohol. If you have um, blue UV lights as well. Like there's kitchen ones that kill all kinds of bacteria and they're not too expensive online. Those are fantastic because these are normally big pieces. You can also start small, but we started big. So yeah, we use some various sterilization techniques to be able to make this happen. And still we got some contamination or lots of contamination in some spaces. So it's yeah, those are some of the hacks that I have found helpful is to use blue UV light or to use bleach, which is not great, but there's really no way to sterilize the individual pieces before you put this together. And normally, one of the ways that you sterilize cardboard is by boiling, which you definitely couldn't do here because then you would sort of make a paper mache rather than making a structure. And so here we have another case study. This is a fabric formwork monolith unit. Basically, to make a fabric formwork, you can do different things. You can sew, as we saw in the first um, little introduction to the section, in scaffolding, and normally in architecture, people tend to use cement to fill these forms. And then once that is completely solidified, the textile surface is taken off. Here you can see many of these modular shapes are being built with just simple wooden frames. And within these wooden frames, there is um, this large sheet of fabric that basically is stapled to all of the sides of the frame so that the shape can be made. So it's just pretty much making a huge like silicone mold or a huge 3D printed mold. But because it's in such a large scale, it just makes more sense to do it with this format. So this is the fabric formwork method. The fabric that they chose to use here is a geotextile fabric that is synthetic. So in this case, the mycelium is contained inside the fabric and won't likely start to grow outside the fabric, like won't use that type of fabric as its food source, although sometimes it does. But in this case, that was one of the reasons for using this, is to try to prevent it from growing into the fabric, because eventually you are using this as a mold, right? They are using this as a mold. So eventually this will be taken out of that mold and will be free from the fabric. And here are some more process photos as to what those shapes look like, and you have more of a reference as to the scale. And to cover them, as you saw in the previous, so in this photo here on the right, you can see the top is sort of hollow. There's this space where the mycelium substrate is going to be entered. And in this photo documentation here on the left, you see that those spaces, or the whole surface, is covered with a plastic tarp. So this is to keep in the humidity, close the lid, so to speak, and yeah, just keep the darkness, humidity, temperature all controlled with that. And now we get to look at some mycoforms. Yay! This is what you saw us work with in the course video with the Grow It Yourself kits. Hopefully you were able to catch that before you landed here. Basically, these little forms here, these planters and yeah, these planters, you can also use these as like candles or candle holders. We tend to do these exercises a lot in in-person workshops, and during the filming of the course, we actually did an in-person workshop where we did different forms, not these necessarily. Students came with their own designs that they wanted to work on and get some insight on, but these are super easy to start, because basically it's like two takeout containers that you can just recycle. Even you can get from your own recycling bin or somebody else's in your neighborhood. You can go uh, dumpster diving if that's your thing, and yeah, make it fun. See what you can do with like recycled Tetra packs and recycled plastic containers. And here are some additives. These are basically flours, starches, and gelatin that help you mold this into a shape, into your desired shape. This is different from cultivation. In cultivation techniques, you don't need to do a lot of the things that we're talking about today. This specifically is to be able to have a better texture, workability, malleability of your material, so that even in these cube shapes, it's important to use that, because the substrate, in this case, it's like these little tiny fibers, right? They're not granular. Doesn't mean that they're going to reach the corners of your mold, but because you're using this whole mix, this composite mix of flowers, gelatin, mycelium, and your fibers, in this case probably hemp, um, then you're going to be able to get into those corner spaces of your mold, so that it's fully myceliated and you don't have some empty gaps in from your mold and your substrate. I wanted to show this project here because I think it's so incredibly beautiful, but also actually really achievable and easy. So here on the left, you have the Minecraft project chair. That's a little bit different, but you can see there are all these modular pieces. Again, they're all these rectangles kind of pieces that have been then placed together as they have myceliated individually, and then placed together in this form of this shape of this chair, sorry, and allowed to grow together. So that's something you can deliberately do. You can half grow all your pieces till they start to show some myceliation. They're not going to break apart as you move them and try to glue them together. Or you can also use some pins to keep them in place, putting the pieces together that need to fit together and glue together. But rather than using glue, you are just allowing the mycelium to grow into the other piece, which it will do. It will just glue to itself. So that's an amazing part of making myco materials. I hope I made that clear. Then to the right, you have this mycelium, which is a really cool project because it's actually just using the negative side, the back side of an IKEA chair as a mold. And it looks super sleek, super beautiful, like it perhaps yeah, was difficult to make, but rather what is more difficult is peeling it out. So make sure you always use some form of cling wrap or maybe even a bit of glycerin on the surface of the plastic chair so that you can pull it out a little bit easier. Because I think that's the hardest part, is pulling it out of that mold, which is rigid, as we mentioned. So imagine a basic IKEA chair that has this shape, and then you take the back side, and this is her process with a different chair. So I just wanted to show it here how easy it is to just grow a form into a pre-existing form. And yeah, just allow your substrate to grow into that exact chair shape, and then very carefully pull it away. I think that's the trickiest part. So once your forms are fully ready to be incubated, they are fully designed, you have gotten your perfect substrate, everything else. Oh my gosh, we're getting to the last stages, and let's have a look at what some of those parameters are. One thing that I want to mention is that there are two potential growth phases when you are making your mold. So, first, you can have your first growth phase, and this will completely myceliate your form. However, the second growth phase, you can take out your piece from its mold and then don't dehydrate it yet, but allow it to keep growing. And the outer edges, the outer surfaces that were in contact with the molds will grow. And normally there's a sort of membrane or skin that can form there, and that can be a nice aesthetic that you're looking for. Sometimes you don't need that. It will definitely make your object more sturdy. But again, this is all up to your discretion and what you want to do. You definitely can just do the one grow phase and then dehydrate. So first, place your molds, my substrate filled mold, in a dark environment of 20 to 30 degrees Celsius. The ideal temperature is about 25 to 27. If you have a way to control that, amazing. If you don't, ideally, at least your space is between 20 and 30 degrees. 30 might be like a little bit high, but if that's just the environment that you're in and it's very difficult to cool down, that's still valid. You can test it out, especially with some heat resistant strains. Then might be more um, that might be more appropriate for your bioregion. So even at 20 degrees, your mycelium will grow and will thrive, but it will be a much slower process. And in that slower time frame of the mycelium taking advantage of its food source, something else might take advantage, which we call contamination or just other organisms. So this may slow down its growth even more, or you may have to toss what you're working with. And mycelium is very receptive to its surroundings, so it's important to keep all of these things under control or monitored. Also, don't move your object too often. The mycelium is definitely receptive to disruption, and it will grow much quicker if it just stays put. If you're not lifting the lid to just like have a peek at it all the time, it's a lot better if you just let it do its thing. So, if at some point in the first week or so you can see primarily white, and again, this will depend on what you're using as your substrate. If it's a grow kit, definitely within like 5 days to 7 days, you will see that. If it's your own mix, this might take up to 2 weeks to fully myceliate, and also depends on the scale. So, if you can see primarily white, with no more brown spots or just whatever color your substrate is. If you can't see your substrate anymore or just very subtly, then it's likely time to remove your object from the mold. So it's fully myceliated. If it's at the top, it's normally all the way through. It helps sometimes to work with transparent molds. So, like the thermoplastic or recycled containers, if they're transparent, then you can actually see if the sides and the bottom are myceliated also. The mycelium will have formed a nice white layer of fluff, or it could be almost like a foamy material on top. This is the membrane. And if there are brown or yellow spots or wet spots on your white layer, then you have waited too long if you wanted to keep it white. However, not everybody necessarily cares about that, and the brown and yellow spots can be just other metabolites that are taking place after the white mycelium has digested its food source. Then some secondary metabolites start to show up in those forms, and it's totally fine. It makes a stronger membrane or outer layer, and it's a nice look as well. So it more or less depends more on your aesthetics and how resistant you want the outer membrane to be. And this is what that looks like with some coco coir. So the second growth phase, as I mentioned, is growing outside of the mold to just get a membrane or skin of mycelium growing on those places that were touching your mold. There is no need to work in a sterile environment at this point. The mycelium is very healthy and strong, and you manipulating it with some gloves is sufficient. Open the mold and carefully remove your object. As I mentioned, it's very humid still and is still fragile. So be careful how you take it out, especially if your shape is in a very, if your substrate is in a very intricate shape, then you want to make sure that you are very deliberate and slow in taking it out because it will break for sure. And you can glue it back together. As I mentioned, mycelium grows into itself. So no harm, no foul. Normally, you can kind of like fix it so that it grows back into itself. But ideally, you're just delicate when you're taking it out. So get a new clean plastic bag or Tupperware, depending on the size of your piece. If it's small, just a Tupperware is fine. Line it with some tin foil so that it will be easier to take off of the base of the plastic. And if it's something bigger, then you might want to use a clean plastic bag to just place it as a dome over your piece. This will keep the humidity, temperature, and all of that contained in like a little microhabitat inside of that bag so that that second growth phase can happen. Then you'll close the bag or close your Tupperware and let the object grow under the same conditions that you did under the first growth phase. And this will take another 5 to 7 days. If it's a really active strain, honestly, even less, like even 3 days. So just have a look at your piece at day 3 and see where it's at and see if you want to stop it there, if you want to see what happens with another few days under incubation. So now that your form is grown and you have allowed it 1 period or 2 periods of incubation, you are going to think about how you're going to dehydrate this piece. And there are a few ways to do this. It depends on the size of your piece as well as just the equipment that you have around. And the first and most accessible, I think, for anybody working with Myco-materials from a DIY kind of practice is to use an oven dehydrator. And you're just going to want to set it between 150 to 200 Fahrenheit, which is 65 to 93. This is like a vegetable dehydration setting. And you're going to lay the mycelium material flat on the baking sheet and ensure the pieces don't overlap because you want everything to kind of be as exposed as possible. Eventually, even you could flip halfway through, you could flip your piece around so that you get the bottom part as well. And then check your material every 30 minutes to prevent that burning or over drying. That's super important, especially if it's a larger piece or, yeah, just a material that you haven't used before. Because even some substrates just tend to hold more water than others. So you might think that you have the timing already down from previous pieces, and then you try something new, and you definitely have to keep an eye and keep documentation. And depending on the thickness and the moisture content, again, this could take like 1 to 4 hours at that temperature. Then, once you are content with the level of dehydration, you're going to remove it and let it cool at room temperature. Easy enough. And this is just a little glimpse at what that sort of looks like. You can see actually here that in this mold there was a plastic film that was placed between the mycelium substrate and the mold. And that's why there are these wrinkly parts. That's actually the cling wrap. So mycelium really forms to the texture that you're giving it, especially not so much the substrate, but once it starts to grow, that skin over top, that skin really grows into all the crevices of your mold. So if this is something you want to avoid, just make sure that you make your cling wrap film, if you're using it, just as smooth as possible. And sometimes it's hard to do, but just a note that this will happen for sure. Next, you have a dehydrator dehydration. It's a bit redundant, but nonetheless, important to say that this is not an oven dehydration. This is with like a conventional vegetable and fruit dehydrator. And you are going to similarly place your mycelium on the trays, ensuring that they don't overlap. Also, as you saw in our video, sometimes you have some of these dehydrators that don't have the door that opens towards you. Rather, they open up from the top and they have trays. So there's a way to hack that. That's pretty DIY, very DIY. Basically, the way that we put them together is like to have something that will support the lid on top. So we took out all the trays in the middle and then put some cans so that the lid would be held in place, and basically stuck some thick plastic film, not just like a flimsy plastic film because that will melt, but a thick plastic film around with just some gaffer's tape, and we're able to use that for bigger pieces that don't fit into those smaller shelves. So that's a way that you can hack it. Ideally, just get a dehydrator that has a door that opens towards you, unless you're just working with membranes, in which case the trays work great because you want the membranes to dehydrate on a flat sheet, right? However, if you're dehydrating membranes, it's important to note that they will shrink and sort of curl into themselves from the outside if you dehydrate them at a really high temperature. Normally, I just dehydrate them at room temperature or in sunlight because the loss of water very quickly from the molecular bonds of the material doesn't allow for like a malleability or a flexibility to be kept. Rather, the material is kind of shocked and it crunches into itself, so it becomes sometimes a little bit deformed. And that's something to note also for these materials, these like myco-composites. It doesn't happen as much as with the membranes because the membranes are just so much more thin and delicate. Yeah, the sides will curl in, so you'll likely lose some of your material if you try to dehydrate them quicker rather than just like wait the appropriate time and do it in a slower and sustained way. So faster is not always better, right? And then the temperature settings here that you can choose in your dehydrator, whether that's for a myco-composite or for a sheet, and then you're going to dehydrate again for like 1 to 4 hours. It could be longer depending on your material, and just keep checking after like the hour mark how it's doing. You'll be able to better gauge if you're going to need like 4 hours or like leave it. In this case, some dehydrators have a setting where you can automatically set the time so it will shut off. If you have that, amazing. Just set it for like 1 hour at a time and keep checking um, until you have that figured out for your material. And then, obviously, once you've documented and know something that works for you, then you can just put the amount of time that you know works for your material, set that, forget about it, and come back to it later. And and then once that's done, then you can get your material out and allow it to cool before you put it away. It's nice, sometimes nice to store these in a tissue paper, or yeah, normally the way that we will store them or ship these around is in some nice corrugated tissue paper. And also interesting to note that, as you see here, these two materials have different skins. So this material here was made with an oyster mushroom mycelium, and it's quite white, it's quite fluffy, spongy, almost how you would think that a oyster mushroom feels like when you kind of squish it. And this material here looks much hardier, has this double layer of skins, and this is Ganoderma. So this is a reishi strain. And yeah, it has formed like its second metabolite sheet where there's like these more brown spots. And that's likely going to happen if you just leave this growing for longer than the period of time that you want this to be growing for. So, like, normally it's fully grown when it's all white, and there you can stop the growth process. If you leave it any longer, it's going to start to create these secondary metabolites. It's sometimes going to have a little bit of a yellow ooziness to it, and that's also okay. That's just these secondary metabolites that are at work. You can also dehydrate your forms with a fan. If they're quite large, this is likely what you'll have to do because they won't fit into your oven or into your dehydrator. So, using a fan right in front of your piece, you can lay them on a mesh tray, you can lay them onto a baking sheet or some waxed paper or tinfoil. So many different things that you can use, but definitely lay something down before you put your material just onto a table or onto the floor or whatever it is. Then you want your fan to be positioned to blow air directly over your material. If it's quite large, obviously just have the head swivel around and ensure that there's good air circulation around the material. So flip it over so that you get the back as well. And this method is definitely going to take longer, not just may take longer, but it will definitely take longer than your oven dehydration. So probably over like a day or more, depending on the material thickness, how large the piece is. So you're going to periodically feel the material to judge how dry it is. And the last way that you can do this is similar to the fan dehydration, but you won't have your fan just open air. It will also take longer. That's why it's similar. So you're going to choose an area with low humidity. If you live like in Barcelona, like we were doing all these experiments, then yeah, there's a lot of humidity. So finding a spot with low humidity is sometimes a challenge, and that's why a fan can help. So also discern what your environmental conditions are, and perhaps open air dehydration is just not something that is good for your piece. If you're in a very humid place, it will just take that much longer for the water to evaporate from the mycocomposite. Then again, you're going to place something to just cover the space where you're going to lay down your piece. Make sure that your material is protected from dust and insects. This is super important. When we were drying this massive mannequin piece, we decided to put it on the roof of our school where we were doing this at the time. and it just got attacked by like dust, pollen. Seagulls ate part of it. So that was a learning process. And yeah, definitely make sure that this is in a space that is covered. I mean, obviously, you can do this inside. The open air dehydration also works really nicely if you have a sunny balcony, for instance, because the sun will help it dry a bit quicker than if it's indoors. But if you're in a space that has just a ton of pollen and dust and insects and all the other things, then you may want to just keep it inside just so that you don't lose your piece to other critters. And then again, just turn the material occasionally, make sure that all the sides are drying evenly. And this will likely take several days. So, especially in more humid environments, as I mentioned earlier. And then you can move on to fruiting if that's what you want to do. So, otherwise, here, once this is dry, you're done. That's it. You're finished. You can decide to do a finish on your piece, or we'll talk about that right after this, or you can decide to fruit your sculpture. This will be before dehydrating. So these are just like two different routes you can take, two different approaches. Basically, either you've done your incubation and you're finished, and that's what you want your piece to look like. So you dehydrate it, you set it in that space, then you can move on to finishes. And or you are choosing to fruit your sculpture, in which case you will not dehydrate it after the first or second incubation periods. You're going to incubate your myco structure, your myco composite, and then you're going to change the atmospheric parameters so that you trigger the piece to want to fruit. So basically, some of the things that we do to keep our piece from fruiting, because normally, as I had mentioned earlier in one of these modules, we're interested in the mycelium side aspect, growing cultivation of mushroom cultivation. We're not necessarily looking at this other set of environmental conditions, which are different for fruiting mushrooms. So that's why this course in particular, these presentations, these recipes are different than what you would see in a traditional mushroom cultivation space. And so we keep our materials in a dark space. We incubate them at higher temperatures. We keep the CO2 levels higher, meaning we don't really disturb our materials, and we don't introduce so much fresh air flow. Like we don't introduce more fresh air to trigger the fruiting of any mushrooms. And these things are important to keep in mind because once you change those parameters, that is when the mycelium, the organism that is the mycelium, will want to reproduce. It will think, hey, this is the perfect conditions for me to release my spores and to propagate myself. So what are those conditions if you do want to trigger the fruiting? You want to, first of all, introduce light to your sculpture. Indirect light is great. If you just are in a room that already has indirect light, then simply taking your pieces out of their incubation space and putting them in another space where the light hits it. Ideally, like a covered space also. So if you just have a clear plastic film, that's great. Where you can just put around like a shelf, that's amazing. And otherwise, then you'll have to do this in another incubation chamber that you can create with a little grow tent. Sometimes they have windows that you can zip open, and so they're still protected. There's like a plastic screen, but you can take off the dark fabric that covers it so that some light enters through. That's one way to do this. And it will depend on your space. And then humidity, you want to maintain a high humidity environment of about 90 to 95%, you can use a humidifier, or you can use this DIY method that we talked about earlier with the aquarium heater in a glass vessel, a large glass vessel of at least holding a liter of water, if not more, just because that water will evaporate. So you'll just have to keep monitoring so that the aquarium heater doesn't evaporate all the water and then it's kind of frying itself. That's also why I mentioned glass, because we've definitely melted some plastic containers with this method and just being a bit neglectful of our pieces and of what's happening with the humidifier. So keep checking every day the humidifier. Depending on how much water it holds, you'll have to check it more frequently. And then temperature, you want to keep the temperature to 21 to 24 degrees, which is different than what we had spoke about earlier. 21 degrees is great. This is like the sweet spot for a lot of different strains, especially ones that we're going to be using for Myco-materials. However, this can change depending on what strain you're using. And so it's always good to double check online. There are a ton of resources and repositories where you can check what your mushroom fruiting conditions should be and adjust accordingly. This is just like an on average, like for oyster mushrooms or for Ganoderma or for, well, horse hoof doesn't really do this, so but that's another strain that we use. So normally we have used Ganoderma and oyster mushrooms to fruit our sculptures, and even lion's mane we've used for some sculptures, and this has also been a little bit cooler, but has also worked in that range. So important to just double check what strain it is that you have and then make the appropriate changes to your temperature. And then you also want to introduce some fresh air, because that carbon dioxide buildup is what prevents mushrooms from growing normally, or if they do grow, they will grow like deformed. So you want to open up your fruiting chamber or your fruiting area, which is what we will call this space. It's not really an incubation area anymore. This is a different space. And if you're keeping the same incubation space for fruiting, then you want to make sure that all the things in that space are going to be fruited. You can't incubate and fruit in the same place. It's they're just a whole different set of parameters. So you should have two different spaces. Or if it's the same space, again, that you're just using but changing up all of these parameters in that space, then make sure that everything in there is going to be fruiting. Then monitor the growth. Keep an eye on your sculpture for signs of pinning. Another note here is that if you are just in your incubation moment, in your incubation period, and you see some pinning and you don't want your sculpture to pin, you can just pick those pins off. And that's another way to just prevent that they grow fully. And this is a photo of what that looks like with a reishi growing almost out of kind of any structure over time. So as you can see on the right, this plate here, the plate is more this white mycelium. It was left incubating for not as long as the pieces on the right. So it's that same thing that I was talking about, this membrane that starts to build around that is more brown and a slightly different texture, like more leathery is a good way to explain it. But both are fruiting. And then this is some oyster mushrooms, and they're just fruiting from the holes. So on the left here, you can see this is just a kind of little plant potter. and it's made with basically two takeout containers, one on the bottom that is that shape, and then one smaller one like these little sauce takeout containers. Then the lid is kind of shaped around that smaller takeout container, so none of those spaces are open. But on the lid, there's a few holes for breathing, for air exchange, and those are the spaces that once the mycelium is ready to fruit, it's going to try to escape. So it's escaping out of those small holes where the air exchange is happening. And so if you're really careful, then you can keep the mycelium there. Obviously, if you just lift the lid, those mushrooms will pull off of your piece. But if you cut around really carefully, then you can keep them in your piece. And it's quite beautiful in a way if you're doing it for artistic reasons, to think of like a plate that can also be your food, and then it can go back to the earth and be a composted material. So there are many ways that you can kind of use the poetics of this fruiting stage. Here's another really beautiful project. This is not ours, but rather Francesca Bonesio did this lamp or this light bulb, and it's super beautiful, growing some oyster mushrooms out of various places. You can see it's quite humid inside as well, so you do have to keep your piece super humid so that this will happen. And that's it there. So those are the parameters that you should keep in mind if you want to fruit. Depending on the substrate and the strain that you have, you might have more or less success with that fruiting stage, and you may grow just like one or two mushrooms or just one or two tiny pins, or it might fruit a ton. So experiment a little bit and read up on your particular strain and what its ideal fruiting conditions are, and that will help you maneuver so that you're able to fruit more if that's what you want. And so now we can look at some finishes. Ideally, you're doing this with a piece that hasn't fruited. It's more difficult to kind of work around mushrooms, but you can totally, because some of these mushrooms you can harvest if you want to actually use them also for like medicine or for food. Then can be like very performance arty, and you can actually have your piece also be food and then still use your piece later. So a lot of different ways that you can go about this. It's not like a black and white situation. And in this case, some of the ways that you can do your finishes is by using a natural resin. In the video in this course, in this module, I shared with you some different kinds of resins and what they look like. We have experimented with everything from synthetic resins to using pine resin, which is only soluble in alcohol. That's important to note. A lot of these tree resins, even Arabic gum, is not normally soluble in water. There's some Arabic gum that is already powdered, and it's meant for food grade consumption, or it's meant for mixing with watercolors, and that has been processed so that it is water soluble. So you just have to add water in that case. But normally, if you buy the stones, the actual resin, you'll have to apply some heat and use alcohol to be able to melt that down to a liquid form so that you can brush it over your piece. And you can do that whether you have sanded your piece or not. Obviously, if you sand your piece, it's going to be a lot smoother, and it's going to make the resin application a lot easier. And yeah, it's going to just look a lot more sleek. You can also use shellac. You can also use liquid glass or liquid silica, and that also works really well. It's normally very liquid and it is going to seep into the material. The material will absorb a lot of it. So you might want to do like 2 or 3 coatings if you want a shinier finish, because the first one will absorb a lot and it is going to leave like a very subtle finish on top. It won't be shiny, it'll just be sealed. And maybe that's all you want. You just want to seal your piece. But if you want like a glossier finish, then you want to add a second layer. And then for pigments and dyes, I would suggest again using pigments like minerals and then adding those to Arabic gum so that you have a better consistency and that you're able to spread it on the surface, kind of like a paint, because the waterier that the substance that you're putting onto your piece is, the more it's going to absorb into the piece. Remember that you just dehydrated it in all the water that escaped. Well, there are definitely spaces where that water can be reintroduced. So if you are sort of drenching your piece in a dye, it's going to absorb a lot of that color and it's not going to look that vibrant. However, if you make a sort of paint or colored resin, then you can keep it better, keep the vibrancy better. Another thing to note that I didn't mention above with the resins is that it's easier to spread these resins if you add a wax. So if you're using pine resin, like for instance, you may want to add beeswax, or carnauba wax is a really good one also to use with pine resin, so that you can spread it a little bit easier, because it's very tacky. It's so sticky, but it's going to leave almost a caramelized finish on top if you do just the pine resin and alcohol, and it's going to be really difficult to get a smooth finish. So adding a wax really helps. And then synthetic resins, also you can add your dyes here, whether they're synthetic or they're natural pigments, and you can color your epoxy or your polyester resin. And it works really well. It leaves a glossy finish and it enhances durability. It enhances water absorption, so it'll be more waterproof. Again, sanding the surface is totally something you can do. You can start with a grittier um, gauge and then move into a more like emery board. You can move into a smoother, smaller gauge. And don't be worried or afraid that you're going to ruin your piece by sanding. You can be delicate to begin with until you sort of like find your confidence with it. But yeah, it works really well. It's a technique that's not going to break your piece apart unless it's already super brittle. But normally, if it's dehydrated, it should be pretty strong at that point. So you can even use a small Dremel, or you can sand it on a belt sander as well if you have a bigger piece, just with caution, but it's possible. You can also decide as you finish that you want your foamy mycelium texture to be left alone. There are some really beautiful, particularly with horse hoof, with Fomus fermentarius, really beautiful textures that are left from the membrane. Very foamy and creamy and beautiful. So yeah, you can keep that as like a organic look to your material. And then also you can cover with other materials. You can decide that this is just the structural material, because structurally also mycelium has a lot of interesting properties, whether you're trying to use it for isolation, whether you're trying to use it for insulation, whether you're trying to use it for to make, well, I'll talk about some of these more speculative applications here, but perhaps you're trying to use it for sculpting, something that is lightweight but also floats, for instance. There's so many different properties that mycelium has, but maybe you don't want that to be your final piece. You just want to use it because of those properties. So then you can always cover it. You can cover it with hemp, flax, bamboo fabrics. You can cover it with fiberglass. If you're making like a surfboard, for instance, you can cover it with a thin layer of clay as well, if that's something that you want to play around with. And even you can cover parts of it and not the whole thing. And again, waxes, you can cover with natural waxes like beeswax or soy wax. Soy wax, again, because it's very liquidy, absorbs through the material a lot. We were making some candles and using beeswax and soy wax, and beeswax worked really well because it tends to cool quicker and it's not as liquidy as soy wax. So it didn't go all the way through the material as we were pouring the candles. However, the soy wax, eventually we had to mix with the beeswax uh, to make it stay, because it was hot and liquidy. It would just seep through the material. And at some point we were like, didn't we fill these candles? And all of that wax had seeped through to the bottom of the material. So important to note that some of these natural waxes, if you're making something like a candle where you're using a ton of that material, then maybe you'll lose some. And if it's just that you're coating with a brush the top of your material and you don't want there to be like another, you don't want it to be obvious that there's another layer of material, then you can definitely use soy wax, because it'll just seep through the top layer and it'll be minimally visible. Whereas like a beeswax, you'll likely notice that there's a bit of a wax finish on it. So many little details to have in mind and to think about when you're producing these Myco-materials and when you're doing your finishes, and experiment with a lot more things than what we're sharing with you here. These are like from our personal experiences and from experiences also of people that we've worked with, or yeah, things that we've read. But for the most part, there's no like right or wrong to experimenting, and you might find something really interesting for your practice that we haven't tried at all. So I encourage that for sure. This beautiful piece here, I want to, now that we are closed chapter on Myco-materials and how to make those as a beginner's approach to all of these aspects of fabrication and design. I want to talk about some different artistic applications and futuristic applications. At the beginning, in the first module, we talked about commercial applications. But I think as artists, designers, and whatever else, some of the more interesting ways to discover is to do some research artwork, really. And it doesn't look like the commercial application from the beginning, right? So I think in order to find some of those more niche places, working with more speculative or artistic applications is, yeah, some of the most interesting work that you can find here. So for a little bit of inspiration, we have this beautiful sculpture here by Jiao Jing. I hope I say their name correctly. It's the Lingzi girl, and this sculpture is from 2017. Again, just with that same process of fruiting your sculpture. This has just been done so beautifully, and the reishi is really growing beautifully. Like you can see it growing from all sides and really maturing and opening up as well, and sporulating also all over this sculpture, which is quite beautiful. So you can also have a time lapse and look at how this grows over time. Some other types of applications of mushrooms, not so much mycelium, but for some of us interested in color, there's the Mushroom Color Atlas, a project by Julie Beeler. It's very user friendly and interactive. It's an online platform that has a bunch of different fungi, a bunch of different mushrooms from a bunch of different parts of the world, and what you can do with them as far as color by adding different pH modifiers and mordants, and by using different fibers as well. And she has documented their a humongous color palette. So either you can search by color that you want to achieve, or you can look up a fungus that's in your region and say, like, hey, what colors can I get with this mushroom? So it's super complete and easy to use. And she also has a repository there with some instructions on how to make lake pigments and how to make paints. And that may be something that's also interesting to you if you want to use that as a finish for your mycelium composite material. And if you click play on this video on the screen here, you will see another really cool application of mycelium and mushrooms is to do some performance art with biodata sonification. Basically, what that biodata sonification is connecting small sensors, really they're small electrodes, that are measuring electrical signals between them. They're like two probes. And I think this is quite interesting already what he's doing, but it's even more beautiful when you make a sculpture and then allow it to fruit. You don't even need it to fruit. You can just make your sculpture and actually place the electrodes into the body of the sculpture before you dehydrate it. This is important because you need the water. Water conducts electricity, and these are two probes that are spaced. Don't put them necessarily beside each other, but space them out a little bit. And what these probes are measuring is the resistance or the disruption of the electrical signal from one of those probes to the other. And that disturbance in the electrical current basically makes a signal that is sent to a computer. And in this case, we tend to use an Arduino. I'm not sure what he is using here. However, I'll show you in the next photo. However, in our case, where we have used this technology mainly with algae, and that's why I wanted to show that other picture of it being used with mycelium, because it can be used as well, is by using this microcontroller called an Arduino. Some of you may be familiar with it. It's like a really easy microcontroller to use. It's like one of the most accessible ones, I think, and one of the most well documented ones. And there's a lot of code as well to use for biodata sonification that you can find on repositories like GitHub. For instance, Electricity for Progress and Nanotopia both have some codes that you can just upload into your Arduino and make this device yourself. So you can see here on the picture on the left, that's somewhat what that process will look like. So we replicated this process with the code that is uploaded there. I think there was a glitch in the code at the time, and we had to sort of rearrange it for the use of a Raspberry Pi, which is a higher level. It's like a mini computer, basically. So I would say, like, start with something easier like an Arduino, and then if you know about electronics and you want to move into something else, what we did for the Future Wardrobe project, which was an algae-based project, but also using biodata sonification, was to create a small computer that basically just served the purpose of creating these signals into sound. And we used the softwares processing and pure data to make that happen in the Raspberry Pi. And the probes were connected to an Arduino Feather. So that's how we were able to connect these two devices. However, the easier way to start is definitely by using an Arduino. And so the probes, the two probes are measuring this disruption between them two, which is caused by different digestive processes, different respiration processes that are happening within a living organism. You can even do this between your two hands, and you will change that that current between the two probes. So as that happens, as that disruption happens, that is turned into a signal. The Arduino will turn that into a number. Then you need to use another software, or you need to directly plug this into a synthesizer. And you can also do it with a digital synthesizer or a analog synthesizer. You can use Ableton for this, or you can use Moog, and both of them work really well for making that number that you're going to get from that disruption of current between those two probes. That number turns into a musical note. So it's not like the mushrooms or the mycelium themselves are making music. That's like a way that we can think about it, but it's not actually correct. What's happening is that electrical current is making a signal. That signal is turning into a value, and that value is turned into a note. And as more of those disruptions happen, and they can be super frequent with mycelium because it has such a high level of humidity and water content in it, a lot of those that movement of water within the organism is happening often. So it's very active, or it sounds very active. However, if you plug these probes into a plant, that movement of water within the plant is much slower. So you'll get a note here and there depending on the plant. It won't be as frequent. So it's also really interesting to do this with different living organisms so you can start to understand how this mechanism works. And so with the synthesizers, then you can either import your own sounds to use as samples, or you can use pre-existing recorded sounds and play around with different pitches and with different resonance, and make your own harmony, co-creating with the organism. Here's the Animoog platform, which you can also use on an iPad, which is why it's interesting, because you can bring it out into the woods and do this there. And you don't need to bring your whole computer. And this on the right of the iPad is the Nanotopia module, which you can also get online. I think she still sells these kits, so you can buy them pre-fabricated, number one, so you don't have to solder all the pieces together and make your own PCB board. But it's a little bit easier if you don't want to go through the trouble. And then some other speculative applications that I just think are interesting to note. This is a really nice project by LD Lazaro, and she was also an alumni of the same program that I've gone to at the Fab Labs. She made these electronic breadboards. So let's go back here just to show. On the left, this is a conventional breadboard, this white object with little holes in it. They're basically, the plastic is isolating the components. so that they don't short circuit between one another. And underneath, there are these metal traces which allow for different connections to happen within the breadboard by placing the positive and negative side of a component in various different parts of the breadboard, like through the little holes, and then being able to create circuits before you create circuits at a bigger scale. So this is for prototyping. And of course, there's a lot of waste that happens there because just in prototyping electronics, there's just so much waste. A lot of these components are made with like cheap labor and also a ton of plastics. And I think this is such a nice application. I'm not really sure why it hasn't become more widely adopted, or not more people have used this, because mycelium, when it's wet, as we saw just before, it carries a lot of electricity between one thing and another because of the water, really, content, not because of the substrate, not because of the mycelium. Yes, the electricity changes because of the digestive and respiration processes that are happening within the living organism as it grows, as it eats, and all of that kind of stuff. However, once you dehydrate the piece, it works the opposite way. It isolates the electrical currents so that they don't travel from one component, from the plus side to the negative side of a component, and you don't cause a short circuit. So this is the exact same idea as the plastic breadboards. There's all the traces that are happening underneath of the little holes with metal that is allowing the plugging in of different circuits. And here you can see how you can even use this not as a breadboard, but in different types of electronics. Here there's just a simple LED circuit where you have an on and off button and a coin cell battery. And this is just being connected together with a resistor there that you can see in the left bottom corner of the image on your left, and with some wire. Nothing fancy, but good proof of concept. And then on the right hand side in the middle, you can see also like a little piece of tape there. You can also use foil tape to keep that wire down. So you can do this in a very DIY way. It doesn't have to be super fancy, but you can create your own little circuits using mycelium as the base to isolate the components. And also you can make some cases for electronics. And this is a case here for the Arduino. So that's also pretty cool. Next, I want to introduce you to some more speculative, interactive forms of using mycelium. For instance, in this case, there is this project called the Unconventional Computing Laboratory at the University of West of England in Bristol. And this project explores the alternative computing approaches beyond traditional binary systems. Basically, researchers are investigating quantum computers and living brain cell-based chips, which offer more diverse ways of representing and processing information. And within that scope of research, which is very nuanced and very specific, they're also using mycelium. And with mycelium, basically what they are doing is trying to decipher if the electrical signals, similar to what we were talking about here with the biodata sonification and the frequencies and spikes, that there is a input and then an electrical output that is happening from the fungus that can be used and harnessed to transport information. So basically what you're seeing here is a bunch of different electrodes were stuck into each of the fungus. So there's different fungus, different species also that were used, and particularly their mycelium, not the actual fruiting bodies in any of these tests. And they were to log the electrical signals, as I mentioned here. And then the time was tracked between the spikes of these electrical signals, as well as the frequency and the amplitude. Like, how strong was that signal? That's what we mean by amplitude. And then these algorithms were compared with the fungi's electrical activity in and human word length, our syntax, and our language complexity. So almost like a Morse code, I would say. This is like the easiest way to start thinking about it. In these electrical signal spikes and their length and the spaces between them, there were almost words that were being formed between by different species of fungi. And depending on the species, also, each of the 4 species that were studied had a unique electrical pattern as well that was interpreted as different languages, which is wild. And the complexity also varied, with an average of around 15 to 20 words. And by words, we're kind of using that loosely at this point, but in a very anthropocentric way, for sure. We can just think of them as like groups of signal patterns, and one of those groupings would be, or one of those collections would be, a word. And they were repetitive, right? So that's how they were able to discern if this was like a particular pattern that was being formed by a specific trigger or a specific input that was being that was triggering those responses by the fungus. And as of now, no translation for this mushroom language has been provided, although a lot of stimuli like food and stress can help discern what each of those groupings of electrical spikes mean. So we can start to discern what inputs are producing which groupings, which outputs, and then start to relate those to a particular symbol or word. In our case, is what we're trying to think of when we're thinking of speculative non-human or interspecies languages, which is super cool. And then as far as biomaterials, this is a really cool example of how one of these sort of more speculative projects has become commercially viable as well. The living cocoon, created at the Delft University by Bob Hendricks, is a coffin made from mycelium that accelerates the decomposition process of decaying bodies. And it's important to note here that these coffins are not living, they are decomposed at this point. They are dehydrated at this point. However, because they're not made of traditional materials like varnished wood and different other materials that are harder to decompose by insects, worms, microbes, fungi underground, when we are buried in those materials, it's hard for our bodies to reintegrate into the environment. However, this material is very compostable, very compatible with living systems. And so it allows the penetration of all of that other life that's going to allow the body to decompose to be much easier. So it improves also soil quality by better distributing those nutrients back to the earth. And the coffin takes about 1 week to grow. This might already be after the material has been grown, and just in the molds, it will take about a week to grow and 2 to 3 years to fully decompose with the body. So this is also important information when you're making your own myco-materials, to do some testing. Even if you don't have access to university machines that can help you figure out the tensile strength or like waterproof strength or fireproof strength or compostability. You can do some of these on your own and just record and repeat the test many, many times so that you can get an average of your results. And I think this is really important, especially if you're trying to create materials and products that can be proof of concept or minimum viable products, to be able to take them to the next stage and to be able to apply for grants, funding, or seed funding. It can be super beneficial to have already done some of that work, even if it's on your own. It shows that you have initiative and that you're thinking about the whole life cycle of the material and the user viability. And then as far as 3D paste, this and 3D printing with different paste, the Blast Studio collection of 3D printed mycelium structures are quite beautiful. I would say there's quite a lot of people doing this process now. I think it's been kind of decoded a little bit. And basically what they do is, and you can look on their website, they actually have a video on their process on how they do this, is break down used coffee cups, which are normally not recyclable because of the plastic lining inside of them. Once you've used them, they are actually trash. So this project is called Lovely Trash. The paper cups are gathered, they're broken down mechanically into smaller bits, and then they're made into a kind of paper mache paste, which is boiled or cooked to pasteurize, and then it's inoculated with the mycelium, that the strain of their choosing. I don't believe that they mentioned what it is. It might be just an oyster mushroom, or it might be a reishi, just because those are normally the most accessible in this biomaterial or myco-material space that we see a lot. And they use quite a large robotic arm and also smaller extruders that are probably made by them or somebody they know. They're not like the clay extruders. They have a big nozzle and a big tube in which they can put a lot of material so that they can continuously print these pieces. And as you can see, the actual architecture of them, again, as we mentioned with the pockets in the termite nest, this is the same idea here. These pockets unfold between outer the outer facade, let's say, of these structures, is creating a micro habitat, a micro environment where the light and humidity the light is minimal, and because there are shadows, and the humidity is retained in the folds. And so it allows for the mycelium to better spread itself and to grow faster with this kind of structure. So it's interesting to also think, again, what the actual structural components, how those can help your mycelium piece grow stronger and faster by just promoting those parameters that the mycelium needs to grow. This is a project that Jessica and I were mentors for or helped out in a little bit. It was from a group of students of EAC in 2019, I believe. And these structures were just basic columns that were being 3D printed by a big robotic arm known as a KUKA. If you come from that lens of architecture, you might be very familiar with these robotic arms and how to use them. Basically, this mycelium project was clay that was just inoculated with different types of mycelium, from oyster mushrooms to reishi, and then printed, and we just kind of saw how they grew. As you see here in this photo with just the clay recipe, it's harder to grow mycelium because clay is not that nutritious. It's more of like a binding or structural agent. It has a lot of minerals and it's a good supplement. However, if we go back for a minute just to look at this beautiful white myceliated structure, most of that is actually paper pulp. And paper is made out of cellulose. It's that sugary carbohydrate that the mycelium needs as its food source to decompose and to grow and to expand. So ideally, if you want more of a structural base, the ideal way to do this is to mix paper pulp in with your clay. So to not just use clay, and sometimes it can also be difficult to just use paper pulp because it can be quite mushy and it's sometimes hard to keep the structure as you're extruding it. So a mixture of paper pulp to clay, and you can use varying percentages depending on what your structure needs. If it's something that's not as high, perhaps you don't need as much clay because you don't need as much of that structure. You can also add xanthan gum. Xanthan gum is a gellant, and this can help you also keep the gluiness or that malleability of the material as it extrudes layer by layer on top of one another, and it doesn't sort of all collapse. So those are some tips and tricks that you can keep in mind when you are making extrudable paste. And I think I mentioned this before as well, but make a small amount of your paste and put it into a large syringe first, like a 20 milliliter syringe, or if you have an even bigger, like sometimes we'll also use the pastry sleeves like for decorating because they have a wider nozzle, and then we can extrude in different shapes and not use as much material as we would use if we were extruding in an actual like robotic arm or a 3D printer. And then we can test out different recipes and see how they grow, document that, and then decide what worked, what didn't work, what we want to try, if we're ready to try at a bigger scale, or if we have to go back to the drawing board and rethink our recipes. So that's a super important step in prototyping with any of these larger scale structures. And here we can see some projected ideas for what these columns could look like. They're quite beautiful. In the left, you can also see this might be like a pink oyster mushroom, and the mushrooms are actually fruiting and coming out. This is just a 3D render, but also starting to, if you have 3D rendering skills, starting to kind of put those together into the story, into the future, speculative future storytelling of your material. It's a beautiful way to get also people involved and people excited about the work and the research that you're doing and its potential applications, and be able to apply for more grants and more funding, because this is kind of a speculative space and it is sometimes difficult with small samples and research to be able to get the funding that you need to continue. So also being able to kind of accompany your work with some kind of renders or sketches or projections and is really helpful and beneficial. And lastly, I wanted to bring this project up because it's quite beautiful. And also, I think probably one of the most speculative, perhaps, but also one of the industries that's like the most well funded out of all of these. So if you're into space travel, this might be a line of research that's interesting for you. This geodesic dome was made by Tosca Turan of Nanotopia. I mentioned her before when I mentioned the biodata sonification project. And she is based in Toronto. I have met her and seen some of these large triangular panels. Basically, a geodesic dome. If you're in architecture, you'll know what this is, but it was a structure created by Buckminster Fuller of sort of the speculative futures school of design. He was an architect and an inventor, And this dome basically can be made modularly with all these different intersecting triangles. And so this is great for mycelium composites if you want to use them as the building blocks, because normally it's not so easy to grow massive structures like this, to just have made like the bottom structure of it, as you see on the right, and just dump a bunch of mycelium substrate on it might not be the best, because not only is it harder to just contain the humidity, temperature, darkness, all of the parameters that you need for the mycelium to grow. Also, it might grow quicker in some areas than in others, because that humidity and temperature can vary from the pieces or the parts that are closer to the ground to the ones that are on the very top of the structure. So it's much easier to break it down into intersecting modules. And in this case, it works well with the triangles. You can make large triangular frames, basically like wooden frames, and grow the material inside of them and then assemble these together. And in fact, this is exactly how she did this. So that is the geodesic dome, which is a kind of proposed structure for building building structures in space. This research project was in collaboration with NASA, and is part of this sort of line of research that NASA has about growing structures in space. And then one of the reasons that mycelium has shown promise as a potential building material for space exploration is that it's lightweight, it's compact, and ideal for transporting to space missions. You can dehydrate it and then rehydrate it and grow it into structural forms, such as bricks or panels, or these modular shapes that are smaller and then can be interlocked to make larger panels and forms and architectures. Also, mycelium can offer insulation properties, so it can be grown. For instance, here in this 3D render, you can see the mycelium would be grown actually like inside of the outer shell of this living structure as insulation. And also, if you're working with radiotrophic fungi that feed on radioactive matter, then you can also use this as protection in space for the people living in this space pod. So I think this is also a really interesting line of research. And that is all for all of our Fungal Matters modules. I hope that you learned a lot of different things, that your mind was open to different possibilities, especially perhaps in this last module where we get into some of the more speculative and not so hands-on kinds of working with the mycelium, and starting to speculate into like future possibilities, and also trying out new, messy, interesting recipes and composites. So thank you so much for joining us on this fungal journey. We are Jessica Diaz and Catherine Uali. You can find us on Instagram in these handles, online formats, digital personas. At Fungal Matters, at Formalized Curiosities is Just, at Slimy Futures is Catherine, myself. And also, if you are in Barcelona, we have a studio there called Symbiotica, Esbiotica. It is located at 14 Paraguay, Calle 14 Paraguay. So if you are around Barcelona, also ping us and come check out the space. And we'll see you in the next adventure.